wrong with that. I tend to do letters that will connect it back to the problem, because when you start doing the more complex analyses, it's helpful to have to go back and, instead of going, wait, which one was weight 1 again? I go, oh, WA, that's the weight of box A. I guess I should tack on forgetting subscripts when they are needed. Unless it's vague. All right, normal force. I have only 2 small objects here, so I got my 2 pairs, weights done. Normal force. Up on A. Is the ground holding it up? Normal force requires contact.
Box B?
Box B, yep. Acting which way? Yeah, down. B is holding box A up. So you're sitting on the couch minding your own business when your older brother sits on top of you. You're not technically feeling his weight, what you're feeling is the normal force he exerts on you. And the way that you can tell a difference between his weight and his normal force, if he starts bouncing up and down on you, his weight's not changing, but you definitely are feeling a difference in the force there. It's the normal force that's exerted. All right, we got 1 pair, we got another, there's another 2 objects that are in contact.
The B in the ground?
Yep. Ground's holding B up, and B is pushing down on the ground. I think last time I talked about equilibrium. What is equilibrium?
When the forces are equal, that acting on an object.
Let's look on the wording. The spirit of what you're saying with the hand gestures, I would say yes, but
Okay.
somebody help out with the wording.
What is zero motion?
Not necessarily.
When the 2 opposite forces acting on an object are the same.
Yeah. No, because if you're saying 2 forces are the same, the directions would have to be the same.
Okay.
I've got like an example of what you did.
What was the example?
You got 10 newtons, on help, and then you got 10 newtons negative on her.
Okay, that would, why is that equilibrium?
Bless you.
Because it's going to equal to 0 newtons.
That, Hunter?
Yeah.
Yeah, Hunter.
Is it because the forces cancel themselves out, or?
Yeah, cancel out, or the sum is 0. The total force is 0. Now earlier when Nathan he talked about them balancing each other out or something like that. He did the hand gesture. Equilibrium, total force equals 0. Or the magnitude of forces that are opposing each other are equal. Before we just said the forces, it's the magnitude of forces. So if A is in equilibrium, then the normal force and the weight equal each other. If they're not in equilibrium, they're not. It's not in equilibrium. So I think I put in a circle there.
Hold on.
Thank you. Let's do that in a second. Here in B, if B is in equilibrium, then the total force is up, which is just as y sub B, is going to be equal to the total force down, which is these two. So the sum of these two would add up to that one, or the magnitudes. All right, let's actually give let's connect this to something real, thus the scale I just brought out. You're standing on a scale. So instead of box on ground, it's person on scale on ground. We will assume that this person is weighing himself on the earth. I'm not going to worry about the building. So I draw my three diagrams here, or my three objects: person, scale, and ground.
Do you want to draw it as good as yours?
You have to draw what?
Draw it as good as yours?
I'm hoping you can draw better than mine. Now the force diagram is exactly what we have over there. Personally, I would change the subscripts, but you don't have to. But I am going to do that for this right here. So I have this y sub p acting up, y sub p acting down, y sub s acting up, y sub s acting down. And then I have weight of person acting down on him, weight of person acting up on earth, weight of scale acting down, weight of scale acting up. And so I've got two weights up, one down. I got boom, boom. So it matches what I have over there, except for I changed the subscripts from A and B to P and S. Actually connect the Y there. So when people are still writing a little bit there. All right, so when I stand on the scale, what does the scale measure? No.
Your gravitational pull on the earth.
No. Most people think scales measure weight. In reality, they don't.
Normal?
Yes. Normal force. Think about this. Look at the three forces acting on the scale. It can only measure forces that are acting on the scale. Scale's not gonna, it doesn't have any Jedi powers and somehow sensing things and the disturbances and force. There's three forces acting here. There's weight of the scale, that's between the scale and the earth. There's normal force acting up from the earth, and then there's this normal force from the person. This is the only force the person is exerting on the scale. This is what it measures. If you're saying it actually measures by weight, then I should be able to put this scale on the ground, step on it, and then as I bounce, I've got all this incredible weight loss and weight gain. Just feel the calories just burning right off and then coming right back. My weight is not changing just because I'm bouncing on a scale. But the needle, well, actually the dial underneath the needle, is zipping back and forth because my normal force is changing. Now, if I stand in equilibrium, if I'm not accelerating, which is the key, it's not a matter of not moving, it's a matter of not accelerating. If I'm not accelerating, then the normal force will be equal in magnitude to the weight. And that's why we can say, oh, it's measuring your weight. But in reality, it actually measures normal force. Questions to hear? Because we're about to do, just so you know, box on ramp. Yeah. All right, let's take 5. We'll come back, we'll do box on ramp. I'm just gonna let the recording keep running, so, if you need me to pause it, or if you need to say something out, so it's not picked up, then either pause it, don't stop it, please. Pause it, or, step outside to have whatever conversation you need. Or let it be recorded for everyone to hear. Yeah, and I was hoping that Brianna would pop back in. Alright, Brianna will pick up. Alright. The famed box on ramp. Anything we can get rid of? Put it away, please.
I guess tension.
Yes, we can get rid of that. If you need to sort of, gosh, box on ramp, what would that look like? There we go, box on ramp. And you people on YouTube will never know what I just did. What else would we get rid of? Did someone say it? I missed it.
How about other?
Alright. And that's it. There's now desired motion. If this cable were frictionless, if it had a frictionless surface, this box would slide. So I still find weight to be the simplest, so let's just start out with weight. Which way on what?
The box going down. Through the ramp.
Alright, box going down. And
The ramp going up.
I'll go with the spirit of what you're saying, on the ramp going up. Now, I have the box here. Technically, the weight is acting from the center of the, is acting on the center of the planet. Well, it acts on every part of the planet, but it sums up to at the center of the planet. So it really doesn't matter where I draw my up arrow, just so long as it's somewhere on this whole mass right here. I do have the ramp as part of the ground. This is what this is indicating, the fact that it's not a separate wedge. So we'll just draw up. Really, other lectures, past years, that you know, could have just as easily drawn it on the surface as in the middle. All right, I have only one small object, so I've got that pair done. All right, let's do normal force next.
Are we using subscripts? Are we using subscripts?
We would use a subscript if we have two small objects.
Oh, so we're not.
So not needed. If you have it in there, there's nothing wrong with it.
Okay.
You going contact?
See it again, Toya?
Is that contact
There is contact between what?
between the box and the ramp?
Okay, so there's a normal force there.
No, the force is going, from the ground is going down, I think, and from the box is going up? No. The box is going down.
All right, first off, on the language, because a number of students will say the force is from. Tell me what the force is on. Which way is it acting on the box?
It's going down, force is acting down on it, contact,
Why down?
because it's on the ramp.
Yeah, but remember, the normal force is keeping one object from going through another.
The ramp. Well, I mean, because if the box is falling, the force is going down, the ramp's not gonna let it go through it. It doesn't-
Okay, so which way is the normal force acting on the box?
Down, maybe down.
Right, so someone just.
Maybe up, then.
The box is not falling straight down, so there's gotta be something keeping it from falling straight down.
Is subject to contact?
All right, the force is coming, incidents now. Normal force requires contact, we have contact. So I got normal force in there, the normal force pair somewhere.
So is this a part of the force of gravity now? Like.
No,
going
it's
like,
separate.
oh, so-
Wait, we're talking about the normal, right?
We were talking about the normal.
So would one be a desire?
The requirement for normal is just contact.
Alright.
But what are the two forces? Which way do they act? Do they point towards each other or away from each other?
Hey, so wouldn't that,
So we're from
yeah,
seven?
one going up on the bottom, and then,
Now Becca several times has said up, and I have sort of ignored that, because there's another direction of normal force relative to the objects.
It would be away, right? Or maybe you said the direction, it would be like opposite to each other.
So okay, they are opposite each other, they are away from each other. Oh, Andre, I thought you had it, I wasn't,
I'm just trying to just see it in my head.
it's not going that way and it's not going that way.
Is it diagonal?
What does normal mean?